All right, welcome. Today we're going to talk about something that drives pretty much every data scientist and engineer a little bit crazy: slow Python code. We're going to show you how to go from those clunky, sluggish, element-by-element loops to the kind of slick, high-performance code that the pros use. This is an absolutely essential skill if you're serious about working with data.
So why is my numerical Python code so slow? You've been there, right? You've got this brilliant algorithm, you code it up, you hit run, and you wait. And you wait some more. Look, it's probably not your logic that's the problem. It's actually a core feature of how Python itself is designed. So let's dig into why this happens, and more importantly, what we can do to fix it.
Okay, just look at this chart. This says it all, doesn't it? On the left, you've got your standard Python for loop chugging away. On the right, you have a NumPy vectorized operation doing the exact same thing. And we are not talking about a small tweak in performance here. This is orders of magnitude faster. This visual right here is the fundamental reason that libraries like NumPy are the absolute bedrock of the entire scientific Python world.
So here's our game plan for this explainer. First, we're going to diagnose the core issue with Python's loops. Then we'll introduce the solution, which is vectorization and its even more powerful cousin, broadcasting. We'll see them in action with a really practical, real-world example, and then we'll finish up with some expert-level tips for managing memory and truly mastering your code's performance.
So let's start at the beginning and really understand the root of the problem. You know, ironically, the slowdown actually comes from one of Python's biggest strengths, its incredible flexibility. But as we're about to see, that flexibility comes with a pretty significant hidden performance cost when you're crunching a lot of numbers.
This quote just nails it. When you're looping over a regular Python list, Python is doing a ton of work behind the scenes for every single element. It has to stop and check the element's type, figure out the right function to call for that type, handle any errors. You get the idea. Now contrast that with a low-level language like C, where an array has one fixed data type, period. All that extra checking that Python does, that's the overhead that just grinds your performance to a halt.
So how do we get out of this performance trap? Well, the answer really requires a shift in how we think. Instead of processing our data one little piece at a time inside a loop, we need to start thinking about applying operations to entire arrays all at once. And this powerful idea is called vectorization.
Now, here's the key thing to get. With vectorization, we're not actually getting rid of the loops, we're just offloading them. We're pushing the iteration process from the slow, interpreted world of Python down into the lightning-fast, pre-compiled world of C. See, because a NumPy array guarantees that all its elements are the same data type, it can just unleash these hyper-optimized C routines to blast through the calculations at top speed.
And this slide just shows you how different it looks in practice. I mean, it's night and day. The code on the left is that explicit one-by-one Python loop. The code on the right, well, that's more than just cleaner code. It's a completely different way of executing. That single line, data times data, is basically you telling NumPy, hey, you handle this. Use your fast C engine and apply this operation to the entire block of data at once.
Okay, so vectorization is fantastic when your arrays are the exact same shape. But what happens when they're not? This is where we unlock what is, frankly, NumPy's most powerful and unique feature, a little thing called broadcasting.
The most important word on this slide is conceptually. See, NumPy is incredibly clever when it comes to memory. It doesn't actually create a giant new array by copying the smaller one over and over. Nope, it just reuses the value from the original smaller array during the calculation. This is why broadcasting is not only super fast, but it's also extremely memory efficient.
To really master broadcasting, you only need to burn these two simple rules into your brain. First, NumPy always lines up the array shapes from the right side and works its way left. Always start at the end. Second, as it compares each pair of dimensions, they're considered compatible if their sizes are equal or if one of them has the size of 1. If those conditions are true all the way down the line, the arrays can be broadcast. That's it.
Let's walk through some real examples here. Take that first case, a 4-3 matrix and a 3 vector. We line them up from the right. The trailing dimensions are both 3. They're equal, so it's compatible. The result takes the shape of the bigger array, 4-3. Now look at that last row. This is the one that trips everyone up. A 4-3 matrix and a 4 vector. We line them up and we're comparing 3 and 4. Are they equal? Nope. Is one of them 1? Nope. So broadcasting fails and NumPy throws a value error. Understanding this specific case will save you so much debugging time.
Okay, the rules are one thing, but let's see how broadcasting can solve a really common task in data science. Imagine you have a matrix of data, and for each row, you need to subtract that row's average from every single element in the row. This is called centering your data, and it's a super standard pre-processing step in tons of machine learning algorithms.
Let's trace how the shapes work here, step by step. We start with our 4, 5 matrix. Then we calculate the mean along axis equals 1, which means we get the mean of each row. This gives us a vector with the shape 4, but wait, as we just learned, a 4, 5 shape isn't compatible with 4, This is the critical moment. We have to explicitly reshape our means vector into a column vector with a shape of 4, 1. As soon as we do that, NumPy can compare 4, 5 and 4, 1. The trailing dimensions 5 and 1 are compatible. The next dimensions 4 and 4 are compatible. And just like that, broadcasting works perfectly.
And the result of all that is that a complicated multi-line Python loop gets squashed down into this single, beautiful, and incredibly fast line of code. And hey, here's a little pro tip for you. Using the keepDimsTrue argument when you calculate the mean is a fantastic shortcut. It tells NumPy to hang on to that second dimension, so it automatically gives you a 4-1 shape instead of a 4. It just streamlines the whole thing.
Okay, at this point, you've got the tools to write fast NumPy code. But to really get to that expert level, you also have to learn to write memory-efficient code. Because while broadcasting is great, the vectorized operations it allows can sometimes hide these little memory traps, especially when you're working with truly massive data sets.
So you might be asking yourself, if broadcasting is so smart about not making copies, what's the catch? It's a great question. And the problem usually isn't in the broadcast itself, but in what happens when you start chaining multiple vectorized operations together.
This slide shows the hidden cost perfectly. When Python sees result equals x plus y plus z, NumPy first calculates x plus y and creates an entirely new full-size array in memory just to hold that temporary result. Then, it adds z to that temporary array, creating a second huge temporary array, which finally gets assigned to result. Now, if your arrays are gigabytes in size, you could easily double or triple your memory usage for a split second, and that can be enough to crash your whole program.
So here are 3 expert-level techniques to get control over your memory. First, use in-place operations. By using the out argument, like in np.add xy out equals x, you're telling NumPy, hey, don't make a new array, put the result directly back into x's memory block. This creates 0 temporary arrays. Second, think about your data types. Do you really need the super high precision of a 64-bit float? If not, switching to np.float32 will literally cut your memory usage in half. And finally, you have to understand the difference between a view and a copy. Slicing a NumPy array usually gives you a view, which is like a window into the original data. It's efficient, but be careful. If you change the view, you change the original array. If you need a totally independent array, you have to explicitly call .copy. All right, we have covered a ton of ground, from the basic problem all the way to advanced optimization. So let's just quickly recap the core ideas to really lock in this new NumPy mindset. Really, it all boils down to these 4 rules. 1. Before you ever write a Python loop, stop and think if there's a vectorized way to do it. Think in arrays. 2. Use broadcasting to gracefully handle arrays that don't have the same shape. 3. Remember that aggregate reshape broadcast pattern. It's a super common and powerful technique. And 4. Always think about your memory. This is the mindset that separates the everyday NumPy user from the expert who writes truly scalable, high-performance code.
So I'll leave you with this final thought. The very next time you're about to write a for loop to work on some numbers, just pause for a second. Ask yourself this question: how can I reimagine this entire loop as a single operation on arrays? Could it be a simple subtraction, a broadcasted multiplication? Answering that question is the first step to unlocking a whole new level of performance and, frankly, elegance in your code. That mental shift is what expert-level NumPy is all about.